Okay. Right. So I hope everyone has time to see the exercises before, just for a second at least. I uploaded them at 5 a.m. Last night because I was on a delayed flight, and yeah, so they're a bit improvised, a bit sort of last minute, but I think they're okay. I hope so. So I threw in some HComp exercises. I threw in sort of a bigger hit exercise, and then I threw in yeah, so that's the hit exercise. It's about binary numbers, and I threw in a structure identity principle exercise relating to the binary numbers, which is kind of similar to what you've seen in the lecture already. So any requests? Do you want to see age comps or do you want to see hits? First one to answer gets to decide. I can try to do both too, of course. I don't know if I can see the chat. Where is the chat? Maybe no one has written. Oh wait, I have to press up here. Sorry. Aha, chat. Cool. It's fine. One simple and then the more complicated ones. Okay. Do you want to see a simple H comp? Is that what I'm getting? Yes. Okay. Well, let me do. I think I can do exercise 1 and 2, and then there's a really hard one that I threw in for the people who love H comps. But we can skip that one, and then we're going to go to the hit one. Okay, so I don't think we have approved this left unit law for path composition. So we want to prove that for a path from X to Y, REFL composed with P is equal to P. Okay, and I think Max showed you how to do this for composition with REFL on the right, but when composing on the left, it's slightly trickier because when we defined path composition, we kind of had a bias on this right path. So we had this comp filler that you could just use to immediately get the right cancellation. For the left cancellation, this won't really work out. So we actually need to build some form of HComp here. But let me start, and you'll see what I mean. So we have a Y and an X, and we have a P. And okay, this is a path between paths. Okay, this is 2-dimensional, so we're going to have to introduce two interval variables. Let's look at the goal now. Okay, so here's what I usually like to do. I usually look at this boundary here. I copy paste it, and I write it in a little comment for myself under the tape, so I remember what's going on. Okay. So this is a square. If I would be really pedagogical, I would also draw the square. Maybe I should do that. Okay, let's do this. So it's not as nice as Anders' square, I know, but so on the, let's say that the bottom here is I, and let's say that yeah, okay, let's just remember the bottom is I, and so the horizontal lines will be the variable I, and there's j going up. So I goes to the right and j goes up. So when I is 0, so on this side here, damn, I made it too small, didn't I? when this side, should have thought about this before. Should have prepared something. Okay. Beautiful. So on the left-hand side here, we have referral composed with P. On the right-hand side, well, it just says, what does it say? It says, sorry, and I'm lying to you again. I just keep. Yeah, sorry. I said that J was going up. So when J is I0, it's X. So actually this side is just referral. X, right? Oh, damn. Okay, bear with me here. Promise I'll be faster with the other exercise. The other side, when J is equal to 1, is just referral at Y. And the bottom side is just, well, what is it? It's PJ. And the top is referral composed with P. Okay, so we have to build a square that looks like this. And the best way to build a square is always to introduce an HComp. So now if I could draw the whole cube, I'm going to build, but I'm not that good with Emacs. Okay, so I'm introducing the boundary here. So to remind you how the HComp works, so whatever I put in here, for example, for I0, whatever term I put in here, term, depending on K, when K is I1, it has to be literally PJ. Did I mess up the directions again? I think I did. Oh, sorry. Wait, here we want something that reduces to PJ, right? Oh no, I'm so sorry. PJ is here, right? Okay, you know what? Ignore my drawing. It's awful. Okay. Okay. Let's just look at what this boundary says. Okay. So when I is equal to I1, and when we need to put in a term here, term K, such that when K is I1, this is literally just PJ. Okay. Okay, but let's start with a complicated term, right? We want to destroy this path composition here. And we only have one way to sort of destroy a path composition. It's to sort of fold this. So let's use the construction. How did we construct path composition? Well, we use this comp filler, right? So comp filler referral P, what is it? It's a path P from referral to referral composed with P over P on the right-hand side and referral on the left-hand side. Well, okay, let's plug in K here and plug in J here. Let's see what happens when K is equal to I1. So I write in I1 here and I normalize, Control C, Control N. Okay, we get an annoying HComp, but this is actually the HComp defining referral composed with P. Okay, so this term is okay. It's going to reduce to the right thing when K is equal to I1. So let's plug it in. Okay, now we need to, now this is going to force us to do things here with the other side, with the other sides. So actually, let's type it in here in the box J equals I1. And let's normalize it here to see what this is. It's, sorry, maybe you can't see this, it's PK. Okay, so here we have Y. But here we see, so when K is equal to 1, our term we plug in here has to be equal to Y. But also the term we plug in here, so it's depending on I and K. So now the boundary condition here is when K is equal to I1, this has to be literally Y. But because this has to respect whatever we put in here, when I is equal to I0, this has to be literally the same as this guy. And this guy is just pk. Okay, so we have a new boundary condition here on this guy. And what I usually do is to just plug in pk and see if it works. Okay, because we know that it has to be pk at some point. And pk was pk when we restrict k to I1. Well, it's actually y. Okay, cool. It seems to fit it seems to respect both this side, and it seems to respect the top condition. So, okay, our pk works. Amazing. This is the thing about HComp. You don't need to think that much, actually. If you have a piece of paper and a pen, you can draw up the cube and make sure that everything works out. I usually just try something and see if I accept it. Okay, so now it's trickier, right? So, well, now we need to plug in. We really want this. We want this term here, depending on k and j. So this term we plug in here when I is equal to I1 has to be literally pj. But also when we plug in, because we've chose pk over here, when j is I1, this has to be literally pk. Okay. In both cases, it's p something. But what? Well, let's try. Is it this? No. Is it? Okay, there are no inversions anywhere, so that can't be it. So there's really only this option we have left. Let's check if it works. Hopefully it does. Oh wow, it works. Okay, cool. Again, you can usually improvise these things quite a bit. And here, okay, we need something that restricts to x when k is equal to I1. Well, let's just try with x. Oh wow, it worked. So why does this work? Well, whatever term we plug in here, when j is equal to 0, it has to be this term. But this term is actually, since you take the minimum of I0 and k, this term is literally just x. Okay, so that's okay. And let's check out what happens when we restrict this term to I0. Oh, that's also x. So actually, x works. And now, okay, so what do we need for the bottom now? Well, we need something that respects all of these terms we plugged in whenever we restrict k to I0. So, okay, this guy was p of I0. Well, it's x. What's x of I0? Well, it's x, so it's constantly x. What's this guy when we restrict k to I0? Well, that's x2. And what's this guy when we restrict k to I0? Well, that was x2. Okay, so actually the constant term x here will work out. Oh my God, I'm sorry. I have had questions in the chat. Crap. Why did I actually give this filler here at all? I have no idea. Okay, but this is important stuff, so I can. I wish I could maybe connect to my iPad. Yeah, of course, it would actually work. Agda, if I just deleted this side, Agda would understand what's going on. I think it can be quite informative to write out this side. Okay. Well, okay, I'm gonna do the let's do the second question now, the associativity question, and I'll try to do a drawing. Okay. Okay, so this one looks scary, but it's actually not that scary. So this says that path composition is associative. So it says that P for P, Q, and R, we have that P composed with Q composed with R is equal to P composed with Q composed with R, but bracketed differently. Okay. This is again a path between paths, so it's going to be two-dimensional. Okay, let's look at the boundary here. Oh yeah, Quiver app. Yeah, that's perfect. Okay, perfect. Let's use that. Okay, let's use the Quiver app. I think I need to change the screen. Okay. So can you see Quiver now? Perfect. Okay, let's actually draw what's going on here. So I'm going to make this the top cube. Sorry, this should go in the other direction. Okay, so the goal was to show that, so what do we have? Can I just add text in Quiver? I guess I can just. The goal was to show that P composed with Q composed with R is equal to, no need for dollars, P composed with Q composed with R is equal to P composed with Q composed with R. Okay. So now you can't see my Emacs, but yeah, of course. Okay. So I have this. I usually use this fancy thing, but it's very useful. Okay. So P was a path from X to Y, Q was a path from Y to Z, and R was a path from what I usually use, from Z to W. Okay. So to show that two paths are equal, well, that's the same thing as saying that we have a cube here, where on the bottom side we have, let me just copy paste. On the bottom side, oh, sorry, we have a filler of a square, where on the bottom side we have this path, and on the top side we have this path here. Okay. And on the left hand side here, we just have REFL. And on the right hand side, we have, to come to that math, REFL. Okay. I'd like to position my text here a bit better. It's ugly. Can do this, I think. Yes, very nice. This is also ugly. Very nice. Okay. Okay, so actually, let's write out what the corners are. So this whole thing is a path from X to Y, Y to Z, Z to W. So this is a path from X to W. And this is a path from X to W too. So on the two sides here, we have just REFL. I guess I should really write actually REFL J. I can even do it better, REFL XJ. This is the cube that we want to fill. This is going to show the identity. Okay. And okay, so what do we have here? We have an annoying massive path composition. Well, so first of all, let's look at the backside first. So I'm going to draw another cube here. No, I would like it to be a bit bigger. Infinite REFL. Oh, maybe I messed up the interval variables again. Which way do I usually think of this? I usually think of I as going to the right and J going up. But
well, I mean, that's fine, but it's not a question of how we think about it, right? It's a question of when we introduced I and J as parameters to SOC, then the associativity proof, then from that point on, they are actually fixed and have meaning, right?
yeah, but you can always swap them when you introduce them, right? So
yeah, but can we just make the diagram and the code be in sync with each other?
Absolutely. So let me look at the code again. So what do I have? I had I0. Ah, crap. Yes. You're right. I did it the other way in the code, right? So okay, yeah, okay, I can swap it. It's cool. Let's swap it. Okay, so let's draw the exact same cube here, but on this side we have and this has to be a J, and this has to be an I, and sorry about this. No, right? Yeah. Oh no, I need to fix these guys now. X. No, sorry, this is W. Oh, this is REFL at W. And this is REFL at X. Okay, is this better? Now it should be.
Yeah,
like,
thanks.
Okay, now it's good. Perfect. Okay. Okay, so let's start with this guy then, the left side of the cube. Oh my god, I really can't do this. Okay. Maybe it's you're better gonna be able to see it now. I should make it this big. I like them big though. Okay. Can I move this somehow? It really doesn't want to move. Okay, that's annoying. Anyway. Oh, tab goes through the non. Ah, that's okay. That's good to know. This is what is this? Well, this is damn, I'm actually starting with the sort of the weirdest side. Let's start with this side instead. The naive cut. But where do I see? How can I? The naive. Oh, it's something else. Yeah. Mhm. Okay. Well, these guys both have something in common. So if we could just get rid of this R here, we would be very happy, because then we just get literally P composed with Q here and P composed with Q on the right hand side. So if we just delete this R from both sides, it would be a very easy problem. Let's look at this side first. Okay, so P composed with Q composed with R. Well, how is this defined? Well, path composition is a filler. So path composition, if I just had P composed with R here, path composition would be defined as a filler with of the square with R on the side here that I'm highlighting right now. It would be constant on this side, and we would just have P down here. So for us, we have a filler of this side, just using the construction of the path composition with on this side RK. Whoops, sorry. We have RK here. We have just REFL of X on this side. And we have P composed with Q down here. So this is this filler we get by definition of the path composition. Okay. Stop me if this feels weird. So what I now claim is that we actually have, okay, but let's fill the other sides first, the back and the front. They're going to be very easy to fill. So the front, there's a lot of X's here already. Let's add another one here. The front, I claim we can fill. We just, if we just put require this side to be refl. Ah, shit, it should be refl k, right? Sorry. And again, just refl down here. Well, then that's a very easy cube to fill. Sorry, square to fill, right? This front is filled by just refl. And we can do the exact same. No, we can't do the exact same thing for the back. Let's wait for the back. Sorry, but the back is also very easy to fill. So let's look at the back. Maybe I should scroll up a little bit. So on the back here, we have W here. And then R went from, oh, what's it now? Z to W. Here we have Z. And here we have, let's require this one to be Z2. And let's label also this side by RK. So let's require that this guy is also RK. And let's require that this side is refl. Oops, sorry. Okay, let's look at the back side now. We have a nice cube. I keep saying cube. A nice square here with refl on the top and bottom. And then we have the same path going up on both sides. That has a filler. The filler of this back side here is just RK. So the back side we have filled the front. The back side is filled by just RK. The front is filled by just refl. The right hand side was filled by definition of the filler for path composition. And now let's look at the left hand side here. So what is the left hand side? So we've kind of restricted ourselves here. We require this guy to be refl. We require this one to be RK. And we require this one to be, well, P composed with Q composed with R. We don't have a choice there. Let's require too that the bottom is P composed with Q, J. If we require this, well, if we require this, the bottom square of this cube, we already have a filler for. So again, it's a square with refl on two sides and the same path on the other two sides. So actually the bottom here, the bottom square here will just be filled by P composed with Q, J. That means that we have our cube now and we're just missing one side. There's only one side with a non-trivial filler, if you want to count the right hand side as a trivial filler, but it's by definition, at least, of path composition. So we have a left hand side here that we need to fill. So it has to restrict to refl here on this side, RK on this side, P composed with Q this side, and then this annoying thing on this side. Let me just make sure this is actually what I did in the in my proof that I wrote up now. Is this the proof I had in mind? I'm getting a bit worried now looking at this. Is it? I think so. Okay, cool. Perfect. Right. Okay. So how do we fill this this front side? Okay, let's draw it out again. So yeah, the left face is not exactly the same as the original problem because of this annoying bracketing of the path composition. So what I could do, so the outermost, so when you apply the path composition thing, you have to deal with the sort of the outermost path composition if you want to apply the filler for path composition. So this would actually give us a filler with P in the base and Q composed with R on this side. So it's not exactly what we want. However,
so my question is, I mean,
yeah.
I understand that, but my question is, like, how have we made any progress? Because the left-hand face seems to be exactly saying what we originally were trying to say. Because if you use the filler of the composition, yeah, like you said, you will get exactly that it's P compose Q compose R.
Yeah. But there is, we have made progress actually, because it was nice that we introduced this RK on this side here, because I still claim that we can sort of suck this path down to P composed with Q along R with a one-liner. And this one-liner will look like this. So let me write it out here. It will be, let's hope that I remember this. I can't see my notes. P composed with sorry, what am I doing right now? Comp filler applied to, oh, that's ugly. I'm sorry about this. Comp filler of QR, oops, QR, K, close brackets, oops, and then this whole thing applied to J. So it's like an app of a comp filler. So you have to think about why this is actually well typed here, because now when you plug in a K here in the comp filler, you actually run the risk of having a dependent path here, or sort of having a weird path with sort of weird endpoints. The nice thing here is that well, it's going to work out actually. So the comp filler QRK will be a path from what is it now, Y to RK. So this composition is actually well defined, and this actually gives you precisely the filler for this side. So yeah, I'm really sorry that I went so fast with the left unit law. I didn't realize I could use quiver, but this was very nice. So I hope this was instructive enough. So that's a nice little trick. And I'm not saying in practice that this is the best way to define the associator in Cubicle Agda. I'm not sure this is actually how we define it in the Cubicle library. It seems to me like this one might actually be a bit hard to work with, but in the future, if you want to prove things about associativity, so like higher paths saying stuff about the path construction we just made, but it's one way to do it, and it's I think the fastest way to do it. So this is now just one H comp. So I hope this was sort of at least half clear. Let's plug in. Let's go back to Emacs and try to. Maybe I can share my whole screen. Actually, maybe we want the cube on the right hand side here. Let's do this. New share desktop. Okay, I have to hide the chat a bit. I have to hide my face there. So, okay. Well, okay. So we have here the associative, the boundary, and we have our cube here. So let's try to just mimic exactly what we just did. So that's an H comp. We had K going up in the cube. And now I have to do this by hand every time. I wish there was a shortcut. I don't think there is one. So, all right. So what did we say? So I naught, that was this side. That was the left-hand side, right? I hope. Wait. Oh no, yeah, it is. Yeah. Okay, good. So I said that was just comp filler. This P composed with comp filler Q R K J. Aha! Wow, it works. And the right-hand side here, well, that was just the usual comp filler or P composed with Q and R and K J. That worked too. And then on the back here, sorry, let's start with the front. That's the next step. The front I said was just refl X. Okay, so refl X, that's just X everywhere. Oh, I haven't introduced X. And the back I said were just RK all along, all along the square. Okay, RK. And now the bottom here, what was the bottom? Well, I said that was just P composed with Q applied to J, because both sides here are refl. Okay. So obviously it's much nicer if you can draw a cube like this. And then you get into 4 or 5 dimensional H comps and you're screwed and you have to do without these drawings, but it's very useful when you can actually make them. But yeah, so this is was a nice exercise, I thought. Cool.
Sorry, I have a question before we move on.
Yeah, absolutely.
So why exactly, like where does it come from that some of these 4 faces we can not give and things still work, but some other faces we have to give? Like I can comment out, I don't know, like the second phase, the I equals I1 phase, and
like this one.
Yeah. So what is going on there?
So that's so to my understanding at least, is that whenever you apply, so let's look at the definition of comp filler. So it's an H fill. So whenever you, wow, my computer is going nuts right now. Okay, whenever you have an H fill there, Cubicle Agda will detect that and will automatically use this H filler. So the issue here is that this, for example, this is not defined by an H fill. So if I remove this, that wouldn't work, because that's actually P composed with, well, an H fill. But as soon as you have an H fill, Cubicle Agda automatically detects it. So it's sort of, Cubicle Agda will do it for you if it's the most natural way of doing things. And the most natural way happens to be when you've defined something by an H fill, it's automatically it automatically tries to sort of apply this H fill and destroy the thing that you define with an H fill. I don't know. That's what a horrible explanation. But does that make sense?
But when you say, I mean, but that's a bit circular, because the H fill comes from the thing we have put there. So do you mean like an H comp was used to define the boundary that we're trying to fill, or?
Yeah. So sorry. Okay. So actually, yeah, this was a bit circular. So the boundary, of course, was P composed with Q composed with R, and this is defined as the top of an H fill. So an H comp. Sorry, I shouldn't have used H fill all this time. I should have used H comp. So the H comp is the top of the H fill, right? So when we have something defined by an H comp, So this is the age comp of defined as the top of comp filler PQR. It's automatically going to look at your construction via this age comp and try to break it down for you in the most natural way it can, which is just saying, okay, this is the top of an age fill, so I'm just gonna if I would remove this here, it's gonna say, okay, since the boundary is the top of an age fill, I'm gonna apply age fill here. That's what it does.
How I would describe it is that, like, if we look at for example, the case when I is equal to 1, then like the age comp we have right now will like reduce by removing the I equals I0 case, because when I is 1, then the I equals I0 case can't happen. And if the resulting age comp is the same as the age comp you want, then you are done. That's kind of how I
I think that's probably what's going on behind the scenes here, actually.
And that would also be what would happen if you have an age fill, because the age fill is an age comp under the scenes.
Yeah, exactly. But in the end, I guess the most informal way of thinking of it is kind of, but that's a great explanation. But the most informal way you can think of it is Agda is going to try to break whatever age comp you have in your boundary down into an age fill. So you can always try and see if it works out. I really like to write out the comp fillers explicitly. That's just my taste here, because later on you might want to prove things about associativity. So there are these like pentagon identities that says things about associativity, and then it's really useful to actually have everything clearly written out, all the sides of your cube clearly written out, because you're going to have to do a lot of algebra with your cube in a higher cube now. So then it's really nice. So I like to write it this way, but feel free to delete sides if you want to. Yeah, I'm sorry I couldn't explain this. I wish I was more of an Agda implementer. I can tell you more about what's going on behind the scenes. I'm very much just a user, unfortunately. Yeah, I hope this is good enough. Okay, let me go back to just sharing Emacs now. This is the one. Right. Okay, let's skip the masterclass in connections here. This is a really hard exercise that I like, but let's not do it. There. Now I can see the comment again. So I click on writing. Yeah. So lambda duck also give a nice solution in the exercise, which is probably actually a much more useful solution if you want to work with if you want to prove things about the associativity law later on. So that one is worth checking out too. Okay, let's do the hit thing here. So this hit exercise is about binary numbers, and I apologize. So this is really not my expertise. My expertise is age comps, even though I'm very bad at explaining them. But now let's do some hits with binary numbers. Okay. All right. So the idea is to describe the binary numbers as a hit. So we're gonna make essentially what is polynomials indexed by with coefficients in Boolean in the Booleans. So the idea is that, well, what is a binary number? Well, it's just a list of Booleans. But then you of course run into this issue that, well, if you have 101, 0, 0, 0, and 101, these should be the same binary numbers, of course. So you don't want to allow for trailing zero, so you want to quotient out, saying that, well, if you have two things that are the same up to trailing zeros, then we should actually say that they're the same. And how do we do this? So what we have here is essentially just our usual list constructor. So I'm going to call it list bin. So we have the empty list of booleans, and we have the list constructor, which takes a list of booleans and adds a new element on the left. And then we say that, so this one is actually enough here. So we say that if, oh yeah, sorry. So I've defined 0b as false and 1b as true. Okay, it was just to sort of get the notation right. We say that, so if 0 as a boolean, the list containing just 0 is just the empty list. Okay, so that this constructor here is now a higher constructor, but this one is going to allow us to, this actually captures this the idea that we want to quotient out by trailing zeros. Lambda writes, I got really confused by pre-EH. Yeah, I can talk about this one later if you want. We can do it maybe off recording. It's one of my favorites. Okay, sorry. Okay, yeah. So we have the, so please stop me, if you don't see why this construction works, or maybe it's clear to everyone and I'm being annoying. But yeah, so the idea here is that we can write these types of things. So with my notation, it's going to be a binary number like is like a list 1b, 0b, 1b. This is going to be the binary number 101. Let's take the one that's not symmetric actually to see which way this goes. So this is 110. So the leftmost item is actually the first item in the binary number, so the smallest. And this is also going to be the same now, thanks to our new constructor, our higher constructor, as something like 0b, 0b. So trailing zeros are shit to us here. Okay. Yeah. Anyway, I also introduced here the number 1 as a binary number, if you want to use that. Okay. So the first exercise is define the successor function on list bin. So take a binary number and define its successor. Okay. So how do we do this? Well, we introduce an x, which is a binary number as a list. And then we do pattern matching on x. This is actually okay. So first we want to define the successor of the. Hang on, aren't the binary digits the other way around? this is very likely. Wait. And no, in fact, this construction gives you. This is the weird thing about this construction. Yeah. So actually, when I was trying to write the solutions to this exercise, I also thought it was the other way around. But this actually gives you the right thing. So it gives you the this actually gives you that the leftmost item in your list is the smallest item. You should remove the leading zeros. Oh wait, but so sorry. Okay, so I wrote this exercise at 5 in the morning. Okay, so did I forget which way the binary numbers go? Yeah, okay, yeah.
It should be much easier to take the successor if they go in the opposite directions.
Right. So the nice thing about this construction is where basically I stole the polynomial construction from the cubicle library and I threw in booleans instead. Okay, I think I just forgot now how you should define binary numbers. See, I'm really not a computer scientist. I'm a very bad computer scientist. Don't you start with the smallest one? So you start with on the left. If you have, for example, 1 1, isn't that the left one? Okay, let's not take 1 1.
But that's the thing, like in your example with 1 1 0, right? It should be the 0 should be the first one because the 0 is the least significant bit.
But when you write a binary number, right? So
you usually write it big endian, just like you do with decimal numbers.
Yeah, right.
And these are little endian. The representation we have is little endian. So
just to verify what I'm
but
saying,
just so we're clear, like this is not a question of notation. There's a real difference here because if you want the trailing zeros to not mean anything, that must mean that the first element of the list is the least significant bit. There's no question of notation at that point.
Well, is this right? Wait, so with my construction, so just please verify now that I have this right. So 1 1 0, that is equal to 2 to the power of 0 plus 2 to the power of 1 plus 0 times 2 to the power of 2, right?
Yes, that's your notation.
Yeah. Okay, so this is
yeah, it's just that usually you write numbers big endian just like you do with decimal numbers.
Okay.
Yeah, so like no one would write the bits like that, but I understand that what you just wrote. So that's okay. Finally, we have some unambiguous notation,
okay.
And that's exactly what the lists encode. It has to be.
Yeah, and now now if you have something like this, right, then it's the same thing, right? Because it's plus 0 plus 0. Oh. Right? It's good, right? So these two numbers we want to equate. Is this correct? Am I making sense?
Yeah, I think it's fine now. Yes.
Yeah. Yeah, I mean, I warned you before I started this that this is not my expertise because I don't even remember how you should deal with binary numbers. But this is the interpretation you get out of this hit. At least this hit was suggested to me by Anders and Max. So let's go with this notation and this interpretation. Then this should really give you the binary numbers. Right. So for the successor, we want to map the empty list, which is just 0, right? To, well, I defined what 1 was. So 0 gets mapped to 1. That's great. And now we have our list case or our cons case. So this x here is a boolean now. So actually this depends now on what x is. So let's pattern match on x. Okay, so this case, for me at least, is 1 is the list 1 xs, right? And this is 0 xs. Okay, so 0 xs, that should obviously get mapped to 1 xs. So that would be so we're adding just 1 to the first position. And now this case is a bit more annoying. So now we want to shift everything to the right. So we want to make sure that the first position is now 0. But that's cool because we can just apply suck list bin recursively to XS here. And this should give you the right thing. And now I need to prove, so now I have this drop I case. So let's normalize the goal. Well, it says, okay, give me something that's true cons empty list and true for I1 and true cons empty list for for I0, and then the same thing for I1. Well, there's not much we can do here. We just give Agda the thing. It's constant. Okay, so that's it. Am I making sense? I'm worried that I messed up this whole exercise now because of this confusion. This is how I learned binary numbers. I don't know. Okay, perfect. Okay, so here's a harder exercise. So let's define addition of binary numbers. This is going to be really ugly, and also prove that this addition has a right unit law. So saying x plus empty list is equal to x. Turns out that you kind of have to do this mutually. So by mutual induction. So to get mutual induction in an Agda, you just write the two definitions you want, and then you write the two constructors directly after each other. So the right unit law shouldn't be hard. I promise you, it's going to be REFL everywhere. But we still need to do this mutually to get this to work. At least I had to. Okay, but let's try to ignore the right unit law now and just define addition of x plus y. So let's first pattern match on x. And let's make things nicer. Okay, so empty list plus y, well, that should just be y. It's an addition after all. Okay, and now we want x cons xs plus y. Well, I promise you there's going to be a bunch of cases here. So let's start pattern matching. Let's pattern match on y to get all the information that we need. So x cons xs plus the empty list, well, that should just be x cons xs. Okay. Okay. Now we have the sort of the main thing here. X xs plus y ys. Now this will depend on what x and y are, right? If they're 0 or 1, or true or false. Sorry, false or true. False is 0, true is 1. Yeah. So let's just start pattern matching here. We get 4 cases. Very annoying, but that's the best way to do it, I think. So let's just expand all the different cases here. You can probably do this in a much better way, but this is what I came up with in my late night session. You don't need to split y if x equals to 0. That is probably very true. Let's not do this. Okay, let's see what happens. I think you do actually. Don't you? Wait, see if I can. Yeah, you're right. I'm of course. Yeah, of course. Yeah, thank you. Yeah, I thought there were a bit too many cases. Yeah, okay, no. Yeah, I should have. Okay, perfect. Okay, but let's do the true excess. This is obviously the most annoying case here when we have 1 in the first position, right? Because then things get shifted. Well, okay, if we have 1, oh, the case x1 should be list bin. Yes, exactly. Yeah. Okay, but if we have 1 something plus 1 something, the first thing has to be false, right? Because, well, it's addition modulo 2 here. But then we need to make sure that this gets bigger somehow, right? Well, let's take suck list bin and apply this to xs plus ys. If you think about this for a bit, you should see that this gives you the right thing. So that's a nice recursive definition. Okay, so what should true true xs plus false ys be? Well, true plus false, that's true. And in the other position here, it should just be xs plus ys, right? And as Lennart pointed out to me here, we only get 1 case here. So false plus y, that should be y in the first position. And then we recursively add xs and ys. Very nice. Aha, now the drop case. I should really fix my solutions that I uploaded then. Very good. And what we want to do here. So I think, so for the drop case, we have to prove that xs plus the 0 list, so not the empty list, but the list with the 0 appended, is the same as xs. And here, this should be given to us by our right unit law that we haven't defined yet. So we have to be careful here that we don't get into a loop, but this should be it. So we just take right unit. We might have to do a further pattern matching later on this to convince Agda that this terminates, but this should be good. So when I 0 here, this is xs, and when I is 1 here, opla, what did I do? Oh no, this is not it at all. Sorry, I have to further pattern match on x. Okay, this is better. Okay, so we want to show that true xs plus empty list is the same as true xs in this case. This is what Agda tells us. We don't need to check why. It's just what Agda tells us, and Agda is right. Well, both of these have a true in them, right? So we can, let's keep the goal here somewhere. Let's keep it here. Both of these guys have a true on the left-hand side. So let's paste it in. And now we need to provide a path from xs plus empty list to xs. But that's perfect. We have our right unit law that we can apply to xs. And it gives us precisely what we want. And I promise you it's going to be the same thing here for the other case, just with a false instead. Exact same construction. So we handle the drop cases. Great. Okay. Now we need to show that the 0 list plus y is equal to y. Okay. For this, I think we're going to have to unfold y. Okay, so this case is just 0 is empty list is equal to empty list. Well, that's our drop constructor. That's precisely the drop constructor. So we're just going to give that. And now here we need to show that xy is equal to xy. Oh wow, I did this in 2 steps before. Ah, yeah, I did this stupidly before. Now it's just, well, it's just constantly xy. So fine. And now we have this annoying thing here. And this is going to be hard to fill for us now because we don't know what this right unit law is. Hopefully this is going to be REFL, but we don't know this yet. So let's wait with this goal and instead go on to define our right unit law. Because we've actually covered all the cases that the right unit law needs. Okay, so the right unit law says that x plus empty list is equal to x. That's pattern match on x. First goal, empty list equals empty list. Nice, that's nice. Second goal, well, some list equal to the same list. Nice, that's REFL. Last case, drop 0i equal drop 0i. Nice, along REFL on both sides. Nice, REFL. Okay. So the right unit law we have now, which is REFL for all the constructors. That's great. And now let's go back to our previous goal here, because now this actually reduces. So now this is the goal. So we have drop 0j here, drop 0i here, and then we have 2 constant paths here. So if you have the same path when I is equal to 1 and j is equal to 1, in that case, what you want to do is you just want to pick the path and you want to take I wedge j. Because this term, when I is equal to 1, this whole thing gets deleted. So this is just drop j, which is what we want. And by, well, symmetrically, of course, when j is equal to 1, this whole thing is just drop 0 of I, which is what we wanted in the j equals 1 case. So that's sort of a rule you can try to remember. So this is a perfect time to apply the min constructor operation, the min operation. Yep. So let's try to give this. Agda is happy. That's nice. So now we have addition. Any questions? I'm actually going to copy paste this into the solutions file because this is much better than the one I had before. Right. How are we doing on time? I guess I don't know how long these usually are. I guess I can do one more. I think I'll skip the structure item to principle because it's incredibly similar to what you've seen in the lecture. I think you should be able to do it. Should we do one more thing with these guys? Wow, I guess we can define the maps back and forth from. I wonder if I would teach an by addition this way. Yeah, it's well, it's cool at least. I mean, as soon as mutual induction shows up, at least you have something cool. It might not be the nicest construction, but it was the only thing, only way I could do it actually. I was trying to do it directly first without doing this mutual induction, but it was hard. So just FYI, I know a lot of people are big fans of hits, and I think this hit is very nice because if we want to capture polynomials, definitely a hit like this is nice because it's very short and it's easy to prove things about. For computations and these type of things, and for a nice concrete definition, I think that the data the non-inductive higher the non-hit version of the binary numbers is much easier to work with. So I don't have a hit bias here. I know Cubicle people might try to convince you to use hits whenever you can, but there's always room for good old regular data types too. Yeah, okay, yeah. So a lot of these other ones you'll prove in the exact same way, just deep pattern matching. The cases, well, you should be able to see what to do for most of them. Some of them are a bit harder. Showing that natural numbers equals to the spin is a bit hard, but it's doable if you have the right lemmas. You can look in the solutions that I've uploaded. I'm gonna make them a bit nicer now because I realized I've been pattern matching way too deep, which is something that happens often. And I'll finish off with a spicy exercise. So this is a bit of a bonus exercise. So don't feel obliged if you're not interested in silly age comp stuff. Okay. So I threw this in. So this is the Ekman Hilton argument in cubical type theory. So the Ekman Hilton argument says that path composition is commutative if you're doing it with the right kind of paths. And so in particular higher paths, so paths from REFL to REFL. There is a sort of a nice proof in standard HOT, which is sort of a basic a standard proof of this in general, and this is a much more general argument that occurs a lot in different situations. But we were staring at this a bit in Cubicle, and we realized we could actually provide a very short proof of this. So, when you do cubical type theory, the only thing you try to do is beat the people who do non-cubical type theory, right? So we have this horrible proof of it that's very hard to read, but it's very short. So I threw this in there as a little challenge. Okay, so let's get started. So, sorry, just want to have the solution here so I don't make any mistakes. So we want to show that if you have two paths P and Q from REFL to REFL, then P composed with Q is equal to Q composed with P. This would be super cool if we could just do it in one line in Agda, but we can't, unfortunately. And this has to do with the fact that composition with REFL doesn't reduce. So for example, P composed with Q doesn't reduce definitionally to P. So while we can't do this thing in just one line, what we can show is that P composed with Q modulo some applications of composition with REFL is the same as Q composed with P modulo some applications of REFL of composition with REFL. Okay, so let's just look at these terms here before we start. So I have a hole here. Just ignore all the other stuff. Let's paste this in. So P, what is P? Well, that's a path from REFL to REFL. Well, if you have a path from REFL to REFL, you should be able to apply REFL to both sides, right? To get a path from REFL composed with REFL to REFL composed with REFL. So that's what this does. It says app lambda XX composed with REFL. So if I apply this to P, I get a path from REFL composed with REFL to REFL composed with REFL. And I can also do it on the other side here. Don't have to restrict myself to composing on one side. This gives something of the exact same type. Is it the same thing? Who knows? Not definitionally, but it's something we can do. Okay, so that's a bit annoying that we have to throw these guys on there. This is not really the identity we want. We want just P and Q here and just Q and P here. But okay. I claim that we can do this in one line. So I've outlined the proof here, but we can maybe do it from scratch. I'll just keep this here. So I've outlined the proof here, and the exercise was just to put in the right connections in the boxes. So let's look at both of these terms. So what do they have in common? Well, on both sides here of this equality sign, we have a composition of two paths. So I've introduced my P and Q here, and I've introduced an interval variable I here. And I want to produce a term here that reduces to this when I is 0 and to this when I is 1. Okay. Well, both of these have this thing in common, that they have a composition in the middle. So I can put that in. Okay. And so actually, what is app of xrefl composed with P? Well, that is lambda j to. Now the constraints Agda gives are not very readable. They are never very readable, sadly. This one you kind of have to ignore them and just try to think about what's going on. This is another way of writing. So this is literally what app lambda x composed with refl p is, right? It's lambda j to pj composed with refl. And likewise, the q guy here on the other side is the same thing, but with refl on the other side and q here, right? And we have the same situation down here too. Okay, so well, we're working on the left-hand side here of this composition. So basically what we want to show is that this is kind of equal to this. Kind of. It's going to be up to a dependent path, but we're going to want to provide a term in here that reduces to this when I is 0 and to this when I is 1. Okay. And so when I is 1, we want this term, lambda j pj composed with refl. And when I is 1, we want refl composed with qj. Well, both of these things again have something in common. It's something composed with something, right? So let's plug this in. So again, I know I'm repeating myself here, but here we wanted pj composed with refl when I is 1, and we wanted qj and refl here. Sorry, that was when I was 0, and when I is 1, we want refl here and qj here. Okay. Then we're done if we with this part of the problem. Well, okay. So when I is 0, we want p here. That means we're going to have to introduce a p here. And when I is 1, we want a q here. So this has to be a q. So now the question is, how can you fill these how can you fill these new holes here with interval variables such that this actually reduces to what we want? Well, okay. Yeah, the hcomp POR is yeah, I know. Yeah, this one is it's horrible to read. It makes me sad too. Okay. Well, one thing we know is that there has to be a j here, because when I is equal to 0, this has to be pj, and when I is equal to 1, well, this has to be qj here. So there will be j on both sides. Aha, and yes, Gergo provided the solution in the chat. So what we need to do now is Yes. Yeah, precisely. So the other side is going to be, yeah. Yes. Let me just, I'm sorry. All right. Okay. So for this to be well typed, first of all, so we know that we're probably going to have to introduce an I here somewhere. A part of the difficulty is that there are two ways to make thing REFL. Yes, exactly. Yeah, but we're kind of forced to use one of them here. Because when I take this path and I restrict, so remember that this whole thing here is a path from REFL composed with REFL to REFL composed with REFL. Oh no, wait, is it? What am I saying? Yeah. Okay. So when j is equal to 0 here, in this guy, we need this to be REFL and we need this to be REFL. Okay, so either this means that since we have a j here, we must make the this disappear. So I claim that we have to put a min here, because what happens if we put if we would put, so this is just some term involving I. If I would put this guy here and we restrict j to 0, then this thing is actually going to reduce to p of whatever we put for the question mark. And we had to have a j, right? It can't be this because there's no inversion on the j appearing in our terms. So we have to have a j, and if we have the max here, restricting j to 0, well, just won't give us the right thing. We need this whole thing to be constant, and instead we're going to get p of question mark. So our only option here is to have j wedge something. And the same thing is going to happen for q. We have to have q wedge something. There's just no other way. Okay, so what can we put in here? So let's think about it for a bit. So either it has to be I, or it has to be the inversion of I, right? Why when j is 0? Because so the boundary here, when j is 0, so if we just spell this out here, so this guy is a so what I've done here is I'm actually only working with this guy, right? Sorry. So what I've done here is I've spelled this out as just lambda j to pj composed with REFL. Oops. And this is a path from REFL composed with REFL to something, to REFL composed with REFL in this case, but we can change that endpoint. But for this whole thing to be well typed, whatever we put in here, well, it has to be a path from REFL composed with REFL, right? So as soon as I introduce a j here and I restrict j to 0, the term I get here has to be REFL composed with REFL. Does that make sense? Yes. Yeah, precisely. Yeah. So that boundary actually forces us to put the mins here, and it's going to be by symmetry. We're going to have the wedges in this box later. Yeah, precisely, yeah. So now our only problem is choosing which I to put in here, whether it should be I or inverse I. Well, there could be other things too that we could put in here, but it seems like the only two reasonable candidates, since we've already used J and I as our only other interval variable that we've introduced. So let's think about it. So what happens if we put an I here? Well, then if we would put an I here, when we restrict I to 0, well, that we'll get a ruffle here. And that's not good. Because if we get a ruffle here, then we have composed with ruffle on the left-hand side in our original path. And it should be on the right-hand side, right? So the only option here is actually to put the inversion of I here, because now when I is 0, this is just pj, the whole thing. I just disappears, and we just get pj. And that's good, because that's what we want. We want this term when I is 0 to be lambda j to pj composed with something. So if I put this just as an I here, this would be ruffle composed with something, and that's not what we want. So the only option for us is actually the inversion of I. And now we have the same problem here for the Q. Now this is going to be much easier actually, because I think what you can do now is you can try both. Agda doesn't like it, and you try the other one, and Agda likes it. But the reasoning is going to be the same actually, if we want to do this in a more rigorous way. So the reason is the same. So if I would put, okay, let's start with the incorrect one. If I would put inversion of I here, and I restrict I to 0, then this whole thing becomes I1. So this whole thing just becomes, the whole thing here on the right just becomes Qj. Wait, is that now I'm confusing myself here. Wait, if I put in an I here, inverse I here, then this whole thing becomes I1. Okay. Yeah, no, we're working with this guy. Yeah. But that means there's a Q appearing, because then this whole thing just reduces to to Qj. But we don't want a Qj appearing, because now we're working with this guy. So that's not good. So our only option here is actually to put an I, because when I is 0, the whole thing here reduces, and we get precisely pj composed with ruffle. Okay, so that's our only option. And also, again, you can just try both and see which one works. Okay, so that handles sort of the path from this one to this one. So yeah, I didn't really motivate why we get this one. I was only thinking about this one now, but well, what happens? Why do we get this one when I is equal to 1? Well, okay, so if I is equal to 1, we get this, and this is equal to this, which is just this. And for this guy, if I is equal to 1, well, it's just this. And what's pi 0? Well, that's just ruffle. Aha, well, that's this guy, right? So yeah, you have to think of, oh shit, sorry, the wrong thing. You have to think about it for a bit, but yeah, try to restrict all the variables and see what happens. Now here's the second part. Now is proving sort of that this side is equal to this side, but now the goal looks weird. So it's P inverse I composed with Qi equals ruffle. Okay, so this is gonna be we're going to do the same thing again. It's going to be P something composed with Q something. I mean, that's kind of forced now. You see it even clearer now why it has to be this, because, well, we have P and Q here. So, well, we have to have P and Q here. Okay, but we know in this case, we know that the right hand, when we restrict J to I1, this term has to be Reffel composed with Reffel, right? And this again forces us. This means that we can only use J max something, because the only way to make both of these disappear, we're not allowed to use inversion of J because there is no inversion of J appearing anywhere. So we have to have J's only, plain J. And the only way to make both of these disappear in the case when J is restricted to 1 is to have J wedge something. Now, what should we put here? Well, it's going to be very symmetric. So reasoning in the same way as we did before, it's going to be just inverse of I here and I here. So this is, the other side is completely symmetric to this side. And this gives you the right path. So I know, I mean, it's a very hard exercise. I hope it was sort of clear enough. Good. So actually, the funny thing about this proof is, I found this proof by normalizing in cubical Agda. So I took an old proof of Ekman Hilton, and I normalized the proof in cubical Agda, and I got this essentially modulo a bunch of junk. So when I came up with this proof, it was not, I didn't really have any mathematical intuition behind it. I was actually sort of given to it by Agda. So I can sort of see why it's very hard to do this, because it's very hard to just come up with something like this. So in my case, it was Agda who came up with it for me. But it's a pretty cool proof, I think. And now, okay, I mean, I can't do this one without doing the full Ekman Hilton, right? We're so close. I guess I'll go over time. So for Ekman Hilton, when I prove that P composed with Q equals Q composed with P, okay. So what is this? I'm only going to introduce 2 variables. Actually, you don't need to introduce. You could introduce a third one, but I actually don't need one. So here's the boundary. Okay, so let's write this as an H comp. And as my hint, I said let's use the pre-Ekman Hilton as the base of this cube. Okay, let's just do it. So I'm going to tell you what the boundary problems are here. I'm just going to write it out first. My God, I hate writing H comps. Ah, shit. There we go. Right. Okay. Both of these sides here are, so let's look at the J0 case. Let's plug in our base and just see what it normalizes to. Okay, that's a bit ugly, but it's not too big. Well, what this actually normalizes to pre-Ekman Hilton at when you normalize this at J is equal to I0, you actually get just Reffel composed with Reffel. Okay, and that's not very strange because it's a path about path from Reffel composed with Reffel is a path between paths between REFL composed with REFL and REFL composed with REFL. So of course, when you restrict j to either 0 or 1, this thing is just going to be REFL composed with REFL. I. Okay, but the boundary is just REFL. So, okay, so the bottom is REFL. We get from the bottom we need this. So when k is equal to 0, we need this to be REFL composed with REFL, and when k is equal to 1, we need this to be REFL. Well, okay, there's only one thing to do really. R unit of REFL. That should be it, right? Oh no. Oh no. Yep. And the same thing is going to happen for j restricted to I1. Actually, do I have the L unit path? Yes, I do. Yeah, because we did that in the beginning. Okay. So now things get harder, because now we need so pre-Ekman Hilton at I0. What was that? Well, let's look at it. It's this one. Sorry, I0 is up here. It's this thing. That's ugly. Let's do it this way. So it's this thing. Well, okay, let me just save this here. Let's actually write out what this is. This is lambda j of pj composed with REFL composed with lambda j of REFL composed with qj. Well, okay. Why not try to delete these REFLs here? Because this is the when k is equal to 0, it has to be equal to this, and when k is equal to 1, it has to be essentially this, just minus the REFLs. Okay, so why not just try to delete these guys? So how we would delete a REFL? Well, we apply, this is essentially app our unit. We apply our unit to pj, and we apply the left unit law to qj. Now, is this going to type check? Maybe. Actually, why does it type check? It shouldn't type check. Did I do the right unit law here? No, I didn't. Okay, sorry. So I forgot to do the right unit law. I'm just going to paste it in from the solutions. We already have a right unit law, right? Oh, no. Wait, confusing myself. Sorry. Ignore what I'm saying. I'm just going to paste it in here. So this was exercise 1B, I think. It was to redefine the right unit law essentially in such a way that this would work. So this is a very complicated definition of the right unit law. I'm just going to throw it in there, which satisfies the fact that if you take right unit of REFL, it's definitionally equal to taking left unit of REFL. Okay, so let's go back to our problem. So now we have this term here. This is kind of strange now. So because, okay, when you look at this path here and you restrict j to I1, this is right unit of REFL. Okay, and when you restrict j to 0 here, then that endpoint has to match up with this endpoint. So when you restrict j to 0 here, this is left unit REFL of k. For these two things to actually compose, we need the right unit law and the left unit law to be definitionally equal when applied to REFL. If I have any other construction of the right unit law that is not definitionally equal to the left unit law when you apply them to REFL, this won't work. This won't type check. So you can try to do this with the old construction of the right unit law, and it's not going to work out. But for us, thankfully, this is going to work out. No. Oh, I forgot to apply. I need to apply J to this. It actually works out. And now for the other guy, it's going to be the exact same thing, just that all the P's and the Q's get swapped, and the right and left units get swapped. But it's, oops, wait, but it works. So it's super dangerous in general to like apply right unit to like introducing an interval variable and then applying right unit to a path that's also applied to this interval variable. It doesn't just allow you to, you can't just delete well, app lambda x composed of REFL applied to P is not equal to P. They're actually of different types. One thing is of type REFL composed of REFL, and one thing is of type REFL equals REFL, right? So it's actually, as soon as you do this type of nonsense that I'm doing right now, you actually get something, a dependent path, right? So actually, this whole thing is going to be dependent path with left and with the sort of, it's going to be a square with the left side being right unit and the right side being left unit. But fortunately now since everything agrees for REFL, we can actually, they actually match up with these sides here. So I'm sorry, I'm going through this very quickly because we absolutely have to stop now. I'm very late. But yeah, I know this one is really hard. This was meant to be really hard. And it's, as always, best to just sit down with it and try to stare at it for yourselves. But I think it's a cool proof, at least. I wanted to throw it in there. Yeah, I'll stop sharing. So any questions or anything before we go? You get yellow? Oh, no. Why? Maybe you haven't defined the. Oh yeah. Also, always specify the point in REFL. Yeah, REFL is occurs in Cubicle like that. Also, make sure you do exercise 1B. Otherwise, it doesn't work out. Or maybe you just do the pre-EH thing. So I feel a bit mean about introducing this exercise, but yeah, it was for those who wanted to do some hardcore HComp and connection hacking. Absolutely not necessary knowledge. Being able to do this hit stuff is actually, which I'm very bad at, as you could see. It's also very useful. Probably more useful actually. Okay. Oh, screen share. Yeah, cool. Wait, what's going on? But what if you introduce X in the context and plug in the X? I think you need to introduce it first. It's an implicit argument. Just so you know, you're muted if you're talking right now.
Plug in X where? Maybe we should record.
Yeah, maybe introduce X first up there. Yeah. And then tell Agda that, and now the X is yellow up there. Oh no, that was just you. Okay. Yeah. Is this better now?
No, seems like it's this and this that complains.
Oh, that's odd. So why is it being cranky? That's kind of strange. So it's cranky for you, but not for me.
And maybe it's because I have a different definition of L unit and R unit. My definition does satisfy the equality, but apparently something else.
That's super strange, actually. Okay, what if you give excess an implicit argument to pre-Ekman Hilton in the bottom?
Mm.
Maybe, you never know. It shouldn't be that though. No.
No,
Okay, what if you give so maybe,
should we stop the recording, by the way?
oh, but I think I have stuff. Oh no, fuck, I haven't. Bye, YouTube.